We use words all day, every day, without really thinking about them. But have you ever stopped to consider the deep, hidden rules that make language work? It turns out that some of the simplest words we use, like every or some, actually created a huge identity crisis for logicians. Today, we're going to dive deep into that problem and uncover how one brilliant thinker, Roman Suszko, gave them a rock-solid definition, completely changing how we see the connection between our words and the world itself.
So here's our game plan for this little journey. First, we'll tackle the confusing problem that was hiding right in the middle of formal language. Then, we'll look at the clever two-part definition that started to clear things up. After that, we'll meet the hero of our story, Roman Suszko, and his absolutely elegant compatibility principle. From there, things get even more interesting as we explore a totally new way of thinking about truth itself. And finally, we'll pull it all together to see what this means for the relationship between logic and, well, reality. All right, let's kick things off with a question that sounds almost too simple. What does the word every really mean? Seriously, think about it. We say it all the time. Every cloud has a silver lining. Every dog has its day. It feels totally obvious, doesn't it? Well, in the super precise world of formal logic, this one little word, and others like it, was a massive, massive headache.
And that brings us right to our first big topic, language's ambiguity problem. This is all about the struggle to pin down words like every, some, or any. In the world of logic, these guys are called quantifiers, and they were causing all sorts of trouble.
So what was the actual problem? Well, it wasn't just a philosophical debate, it was a structural one. Logicians from what's known as the love of Warsaw school realized that in their formal systems, these quantifiers didn't have a clear grammatical home. They were just ambiguous. Imagine trying to build a high-precision Swiss watch, but one of the most important gears doesn't quite fit on any of the posts. The whole machine just won't work right. That's the kind of fundamental flaw they were dealing with.
So what do you do with a word that doesn't seem to fit anywhere? You don't just give up on it, you build a proper place for it. This brings us to the next step in the solution, a two-part definition. The big idea was to stop treating quantifiers like these mysterious single things and instead break them down into their component parts.
Okay, think of a quantifier like a recipe for creating meaning. It's not a single ingredient. It's a function that needs two specific things to work. First, you need the variable. That's the specific thing you're talking about. In the phrase every cat, the variable is cat. Second, you need the scope. That's the context, the phrase where the variable is doing something. So if the scope is likes to nap, you've got your two ingredients. Only when you put them together do you get a full thought. Every cat likes to nap.
And once you have those two ingredients, your variable and your scope, you can finally give the quantifier a proper denotation. Now, that's a fancy-sounding word, but all it really means is its official, precise meaning. Suddenly, a word like every isn't this vague, floating concept anymore. It's now strictly defined as a function that takes two inputs and gives you one clear output. The ambiguity just starts to melt away.
But just having the right parts isn't quite enough. You need a master rule to make sure they always fit together perfectly. And this is where the hero of our story, Roman Suszko, steps onto the stage with his compatibility principle. This is the real key that unlocks the whole puzzle.
So here's Suszko's big idea, and it is just beautiful in its simplicity. He said that for any logical language to be truly consistent, its grammar, the syntax, and its meaning, the semantics, have to be perfectly compatible. They have to fit together like a key in a lock. A word's role in a sentence has to directly mirror what it means out in the real world. No exceptions.
And this wasn't just a theory, he put it to work. His principle was designed for these super precise systems called categorical languages. And in those systems, his principle does something amazing. It builds a direct bridge between a word's syntactic category, that's its grammar job, like being a noun, and its ontological category, which is just a fancy way of saying what kind of thing it is in reality. And with that bridge in place, bam, you've got a definitive, formal solution to the whole quantifier mess.
Okay, so the technical problem is solved. Check. But this is where the story takes a fascinating turn, because in solving this puzzle, Suszko and his colleagues kicked open a door to something much bigger, a really profound philosophical shift. This brings us to our next section, moving beyond true or false and into the world of non-Frigiean logic.
This chart just lays it out perfectly. For a long time, the main view in logic, which came from the philosopher Frege, was that a sentence is basically just a name for one of two things, true or false. It's like a light switch, right? It's either on or it's off. But Suszko said, wait a minute, That's way too simplistic. He argued that sentences do something much richer. They don't just point to an abstract value, they refer to actual situations or states of affairs in the world.
And these situations he was talking about, they have a formal name, semantic correlates. So in this new non-Phrygian world, when you say, it's raining outside, the meaning of that sentence isn't just the abstract idea of true. The meaning is the actual real-world situation of water falling from the sky. Logic suddenly became a tool for describing reality in all its messy detail.
Now, being a logician, Suszko didn't just leave this as a cool idea. He built an entire formal system around it. It's called the sentential calculus with identity, or SCI for short. And that last word there, identity, well, that's the real game changer.
Because in his system, the equal sign gets a major upgrade. When you write A equals B in SCI, you're not just saying that sentence A and sentence B happen to both be true. You're saying something much more powerful. You're saying they refer to the exact same situation. So the sentence "the morning stars in the sky" and "the evening stars in the sky" could refer to the identical state of affairs, the planet Venus being visible. It's a whole new level of meaning.
So what's the big payoff for all this work? Simple. You get a logic with far greater expressive power. You're no longer just shuffling trues and falses around like a calculator. Now you can build a logical system that can actually reason about the very situations and events that make up our world. It's a huge leap forward.
And this brings us to our final destination, where we tie all these threads together, logic and the world, and what Suszko's incredible solution really means for all of us.
All right, let's recap the whole journey. We started with this shaky foundation, where words like every were causing all this ambiguity. The first fix was to define them properly, as a neat two-part function. Then, Roman Suszko came along with his masterstroke, the compatibility principle, insisting that a word's grammar and its meaning have to be a perfect match. And we learned that this whole brilliant solution stands on a revolutionary idea, that language isn't just about true or false. It's about describing the real, tangible situations that make up our reality.
So a journey that started with what seemed like a tiny grammatical puzzle has led us to a profound new way of thinking about meaning itself. We've seen how a formal system can be designed not just to calculate, but to actually describe the world around us. And that leaves us with one last big question to chew on. If logic can describe situations, what else can it describe?